In this session, we're going to look at Bayes' rule. And in fact, we came up with Bayes' rule on our own without calling it Bayes' rule several times in the previous set of problems. And then we'll apply Bayes' rule to similar types of problems that we were doing from before. Okay, so let's suppose that we have non-empty sets B1, B2 up to Bk, which are a partition of S, and the probability of any given Bi is not equal to 0, and A is an event such that the probability of A is also not equal to 0. Okay, so let's start with the conditional probability of one of these sets in the partition B sub r. So the probability of B sub r given A is by definition of conditional probability the probability of B sub r intersection A divided by the probability of A. Now recall the law of total probability. So probability of A can be replaced by summation I equals 1 to k probability of Bi intersection A, right? That's the law of total probability. So, and because the Bi are a partition of S. Now, if we use the multiplication rule, right, then we can replace probability of Br intersection A by probability of Br times probability of A given Br. And we can replace probability of Bi intersection A by probability of Bi times the probability of A given Bi. Okay. So that's basically Bayes' rule. The probability of Br, one of the sets in the partition, given the event A, is equal to the probability of Br times the probability of A given Br, divided by summation I equals 1 to k probability of Bi times the probability of A given Bi. Okay. Now, one place where this might come up, for example, would be supposing that you were given, it was easy to work out the probability of A given Br, but what you actually wanted was the probability of Br given A. Then you could use Bayes' rule to help you work that out. Okay, so let's try this. So supposing that you have, supposing that 0.1% of the population has Doofenshmirtz syndrome, and the test for DS gives a positive result with probability 98% when DS is present, and a negative result with 99% probability when DS is not present. So the probability of a test reading positive given the disease is 0.98. And the probability of the test reading negative with when the disease is not present is 99%. Okay. So what's the probability that someone who tests positive has the disease? This is something that doctors routinely overestimate. Okay, so if we let D be the event that a person has the disease, let T be the event that they test positive, what we are being asked for is what's the probability that the disease is present, D, given that T, the person that's tested positive. Okay, so what have we been given? First of all, let's write that in this notation of probabilities and events. We've been given the probability of that any random person off the street that we pick up, there's a 0.1% chance that they have the disease. The probability that a person will test positive given that they have the disease is 0.98, and the probability that they will test negative given that they do not have the disease is 0.99. Okay, and what do we want? Right? So we have probability of t given d, and we have probability of t complement given d complement. But what we want is probability of d given t. Right? And Bayes rule can help us to do that. Okay. There's a few other things we can work out. The probability of d complement, the probability that someone doesn't have the disease, any random person, is well, 0.1% of the time, right? 0.001 of the time, people have the disease. So the rest of the time, 1 minus 0.001 is 0.999. So if people have the disease 0.1% of the time, then they don't have the disease 99.9% of the time. Okay. Now, the probability that when a person has the disease, when people have the disease, 98% of the time, they will test positive. So that means 2% of the time they will test negative. So 1 minus 0.98 is 0.02. That's a probability that they will test negative for the disease, even though they have the disease. Okay. And the probability that they test when people don't have the disease, then they test negative for the disease 99% of the time. So that means that when they don't have the disease, 1%, 1 minus 0.99, 0.01, 1% of the time, they in fact test positive even though they don't have the disease. So these are things that we can determine. Now we can have a partition. We have D and D complement as a partition. Any event E and E complement would partition the sample space as. Okay, so what do we want? We want the probability of D given T. Okay, by our definition, that's probability of D intersection T divided by probability of T. My multiplication rule, it says the probability of D intersection T is the probability of D times the probability of T given D. And in terms of total probability, we write out P of T. That's using this, right? Partition of D and D complement. That's probability of D times probability of T given D plus the probability of D complement times the probability of T given D complement. And we have all those numbers. So we put those in and we get 0.08933. Okay, so 0.1% of the population has the disease, but given these rates for testing positive and negative, if the person actually tests positive for the disease, then there's an 8.933% chance that they actually have the disease. Okay, let's try another example. So there are 3 suppliers of positronic brains. Call them supplier 1, supplier 2, and supplier 3. 3% of the brains supplied by supplier 1 are defective. 5% of the brains supplied by supplier 2 are defective. And 4% of the brains supplied by supplier 3 are defective. Okay. So we order 5,000 brains from 1, 3,500 from 2, and 2,000 brains from 3. They're all placed in the warehouse, all mixed together. I can't tell which one came from which. Supposing I take one out of the warehouse and I test it, what's the probability that it's going to be defective? Okay, so some events that are of interest here. S1 means that it came from supplier 1. S2 means the brain came from supplier 2. S3 means it came from 3. S1, S2, and S3 are partition set. D means defective. D and D complement would also partition the sample space. Okay. So let's see. Total number of brains we ordered were 10,500. Okay. So the probability of S1 is 5 out of 10.5. Probability of S2 is 3.5 over 10.5, and probability of S3 is 2 out of 10.5. I remember we ordered 5,000 out of 10,500 from one. We ordered 3,500 out of 10,500 from S2, and we ordered 2,000 out of 10,500 from S3. So these are the probabilities that they came from supplier 1 or supplier 2 or supplier 3, any given brain. Now, the probability that the brain will be defective if it came from S1 is 3%. We were given. The probability that it would be defective if it came from S2 is 0.05. The probability that it would be defective from S3 will be 0.04. Okay. So from total probability, remember S1, S2, S3 give a partition of the sample space S. So the probability of D is the probability of S1 times the probability of D given S1, plus probability of S2 times the probability of D given S2, plus probability of S3 times the probability of D given S3. Now we have all of those numbers, and we put them in, and we get like 3.86% is the probability that any brain will be defective. Now let's try another problem. And so the same setup. And now we're asked that supposing that a randomly selected brain is defective, what is the probability that it came from supplier 1? Okay, so what is the probability that it came from supplier 1 given that it is defective? That's the probability of S1 given D. Okay, so if we apply Bayes' rule, that's the probability of S1 intersection D divided by the probability of D. Okay, but we worked out what the probability of D here. D is, that's this. And that's this number over here. And the probability of S1 intersection D by the multiplication rule is probability of S1 times the probability of D given S1. So once again, you put in all those numbers, and you will get 0.37. So those were some simple applications of Bayes' rule.